Hello students. Welcome to the YouTube channel, Physics Simplified. Here, we will understand numerous concepts of physics from a numerical perspective. So, without any further delay, let's jump into the discussion. Topic of discussion for today's video: force between two parallel current carrying conductors. In this problem, we have two long parallel wires, separated by a certain distance, carrying currents of equal magnitudes in opposite directions. These two wires are suspended from a rigid support with the help of four cords, each of equal length L, from 2 points, O and O' respectively, as shown in the figure. If the mass per unit length of the wire is given by lambda, we need to determine the value of the angle theta made by each cord with the vertical. Given the value of theta is small. Let us now identify the concept required to solve this problem. The whole system is in equilibrium, so net force acting on each current carrying wire is 0. It is denoted by summation of vector F equal to 0. Here, each conductor lies in the magnetic field set up by the other, hence, each experiences a magnetic force exerted by the other. Let us visualize the whole situation, where we have considered two straight parallel wires are carrying different currents in opposite directions and are placed one above the other. According to the figure, the current I2 in the lower wire creates a magnetic field B2 at the position of the upper wire. The field B2 points into the paper. So, it is perpendicular to the current I1. It is the field B2, due to the lower wire, that exerts a magnetic force on the upper wire. Using the right-hand rule, we find that the force on the upper wire is upward, thus repelling it away from the lower wire. We can apply the same logic for the current problem also. Remember that the magnetic field of the lower current is not a uniform field, but it is the same at all points along the upper wire because the two wires are parallel. Let us now set up the steps and equations to solve the problem. The force diagram for the two wires at the point of suspension O or O' is shown in the figure. We will discuss all the forces a bit later. As we know, each of the two wires experiences a magnetic force exerted by the other. The magnitude of the magnetic force per unit length between two long straight parallel current carrying wires is given by F' is equal to μ0 by 4 pi times 2I1 I2 divided by d. μ0 is the permeability of free space, I1 and I2 are the currents in the first and second wire respectively, and d is the distance between the two wires. According to the problem, both the wires carry currents of equal magnitudes. If we consider both I1 and I2 to be equal to I, then the equation modifies to F' is equal to μ0 by 4 pi times 2I squared divided by d. In the given data, mass per unit length for both the wires is given. If we consider length of each wire as L0, then mass of each wire will be mass per unit length multiplied by length of the wire. So, mass of each wire is equal to L0 times lambda, where lambda is the mass per unit length. Let us now analyze the force diagram in detail. Before doing that, let us consider the front view of the given arrangement. Considering the wire on the left as our first wire and that on the right as the second, we find that current through the first wire is away from us. So, considering the front view, current through the first wire is directed into the paper and hence is symbolically represented by encircled cross. Since current through the second wire is towards us, so, again considering the front view, current through this wire is out of the paper and hence is symbolically represented by encircled dot. Now, let us find the forces acting on the first wire. Remember, we can do the same for the second wire by following the same logic. Since the two parallel current carrying wires are exerting repulsive force on one another, hence, they are separated by some distance. As a result, tension acts in every chord, by which the two wires are suspended from the rigid support. Tension always acts along the string towards the point at which it is rigidly clamped, hence, in this case, the tension acts along the chord towards the point of suspension. It is denoted by T, weight of the wire, that is, mg, which acts vertically downward. These two above-mentioned forces are also same for the second wire. Now, the total magnetic force exerted by the second wire on the first, denoted by F, is towards left, that is, away from the second wire, because the force is repulsive in nature. For the second wire, the direction of this magnetic force is towards right, for the same reason. Since the entire system is in equilibrium, net force acting on the first wire must be zero. This means, net force is equal to zero, both along the horizontal and in the vertical direction. Mathematically it is written as, summation F suffix horizontal is equal to 0, and summation F suffix vertical is equal to 0. The same is applicable for the second wire also. To find out the conditions for horizontal and vertical equilibrium of the first wire, we need to resolve the tension in two rectangular components. Applying the concept of resolution of a vector, and using the geometry, we find that the vertical component of the tension is equal to T cos theta, which acts vertically in the upward direction, and the horizontal component is equal to T sin theta, which acts towards right. For vertical equilibrium of the first wire, the vertical component of tension must balance the weight of the wire. So, for vertical equilibrium we have T cos theta is equal to mg, therefore, T is equal to mg divided by cos theta. Now, for horizontal equilibrium of the first wire, T sin theta must balance the magnetic force. Therefore we have T sin theta is equal to F. Substituting T in this equation and simplifying we get F is equal to mg tan theta. Substituting the expression of m, the equation changes to F is equal to lambda L0g tan theta. Since F is the total magnetic force, hence F is equal to F prime times L0. Therefore, F prime times L0 is equal to lambda L0g tan theta. Substituting the expression of F prime, we get mu 0 by 4 pi times 2I squared L0 divided by d is equal to lambda L0g tan theta. Let us mark this equation as number 1. By problem, length of each chord is L, and the angle made by each chord with the vertical line at the point of suspension is theta. This vertical line is also the perpendicular bisector of the line, denoting the separation d between the wires. From the right-angled triangle, we get sin theta is equal to d by 2 divided by L. So, d is equal to 2L sin theta. Substituting d in equation 1 and simplifying, we get sin theta times tan theta is equal to mu 0 by 4 pi times I squared divided by lambda Lg. Suppose this is our equation number 2. By problem, the angle theta is small. We know that for small values of theta, sin theta and tan theta are individually almost equal to theta. Using this approximation, we get from equation 2, theta squared is equal to mu 0 by 4 pi times I squared divided by lambda Lg. Therefore, theta is equal to I times under square root mu 0 by 4 pi times 1 divided by lambda Lg. This is the answer to the problem.